Hi everyone, so in this video we talk about Poisson distribution. This distribution actually models the number of times an event occurs in a fixed interval. It can be time, it can be space, and it is written like this: x follow a Poisson distribution with one parameter which is lambda. What is this lambda actually? It is the average rate. Okay, this is the average rate. I will explain it with an example. Now, what is the probability mass function when we have Poisson distribution? It is actually written like this. This is the formula. So px equals a specific value. This is PMF. It is the exponential minus lambda. We said lambda is the average rate. We will see this in an example. Times lambda power x divided by x factorial. Now let's see how we got this formula. I will give you an example. Imagine I have interval of time, let's say 1 hour. This is an interval of time of 1 hour. I know that in average four buses pass through station, okay, in this interval of time of 1 hour. So how can we convert this to binomial? What does this mean? Imagine I try to first, I know that this is a time, this is time. So inside this interval of 1 hour I have infinity of values, but let's say I divide it into minutes, for example, just to illustrate how it works. Let's say I have 60 minutes. So it's like I have the first minute, either a bus pass or not. So I have this binomial or Bernoulli trial, right? So it is either yes or no. For the second minute, the same thing. Either I have a bus or no. So it is exactly the same concept as binomial, but here I said it's not about minutes, it's not about second, but I have infinity of trials. So it is binomial with infinity of trials. Okay, so keep this in mind. Poisson distribution is a binomial with n equals infinity, or infinity of trials. We said we have this lambda. Lambda here replace exactly the expected value, the average expected value in binomial. So lambda is the same as expected value, which is n times p. So the probability in Poisson distribution is actually lambda divided by n. Okay, lambda divided by n. So let's replace what we learned here. So we know that p is lambda divided by n. Q is 1 minus p, which is 1 minus lambda divided by n, times, we know that the combination x from n is the factor of n divided by n minus x factorial times x factorial. So this is our formula for when we have a Poisson distribution. But we also know that n is infinity, right? So the limit of this when n tend to the infinity is simply this. We get this. No need to go deeper in math, but the limit of this is this, and this is our formula. So from now on, if you know that we have a Poisson distribution, so the PMF, the probability that x takes a specific value, is simply the exponential minus lambda, which is the average, times the lambda power x, the number of success, and divided by x factorial. Now for the expected value and the variance. For expected value, we said that it is actually the average, which is lambda, and in Poisson distribution the average or the expected value equals as well the variance. Okay, so lambda is the expected value, it is also the variance. So now let's solve an exercise to make it clearer. So let's apply what we have learned here in an exercise. So this is our exercise. We have we know that the average number of emails received per hour is 4. So this is the average. So lambda is 4, and we know that x number of email in the next our random variable is the number of email in the next hour. So we know that x follows Poisson distribution. We write it like this with one parameter which is for the lambda. Now the question is to find the probability of getting exactly 2 emails in 1 hour, so in the next hour, so in 1 hour. So we want this px equals 2. What is it? We apply our formula. We replace here lambda by its value, which is 4. We replace x by the 2 here. It equals x equals 2, and we calculate this. We get 0.1465. So this is the probability of receiving 2 emails in 1 hour, the next hour. And the expected value and the variance, we said expected value equals the variance in Poisson distribution. It is lambda, so it is 4. Now if the question is px greater or equals x, so how to find this? Simply we convert this to less than. So we know that to convert this to the less than, so we have px greater or equal x. It's actually 1 minus px strictly less than 2. Okay, so px here greater than 2. So it is since here it is greater or equals, here it becomes strictly less. If it is strictly greater, here it becomes less or equals. So what is here px less than 2? What are the value of x less than 2? Either it is 1 or 0. That's the value is less than, strictly less than 2. So this becomes 1 minus p of x equals 0 plus p of x equals 1. We calculate p x equals 1 by replacing here x by 1 and lambda by its value, and we calculate px equals 0. Also we replace here x by 0 and lambda by its value, which is 4, and we get this. So the answer for our question is the probability of getting 1 or more than 1 email for the next hour is 0.9085, which is 20.85%. Now let's see this. What is the probability of receiving exactly 2 email, but this time within 30 minutes, not in 1 hour? Our lambda actually is 4, but for 1 hour. So for a half or for 30 minutes, our new lambda is we multiply it by t. Time here is the half, so 30 minutes is 0.5 of 1 hour, so we multiply it by 0.5, we get 2. So we replace here our lambda, instead of 4 we replace it by 2 actually. So we replace lambda by 2, we replace x by 2 because we want px equals 2, and this is the result. So the probability of receiving 2 emails in the next 30 minutes is 0.27 or 27%. So we will finish this video with the approximation. As we saw in the beginning of this video, we said that the Poisson distribution is simply the binomial with infinity of trial. So we can do approximation. When we have binomial, we can, instead of binomial, we can use the Poisson distribution. But when we have two conditions, the first, n tend to infinity, it's very large, and the probability is too small, so it tends to be 0. And of course the product gives our lambda, which remains finite. Okay, and we have actually a rule of thumb that says when we have n, the number of trial, greater than 20 and our probability is less than 0.05, we can use the approximation. And for more accuracy, n must be greater than 100. Let's see this with an example. So imagine I have a machine that produces items, and each defective with probability of p equals 0.001. From n items, the number of trials here is n equals 2000. The expected number of defective here is expected value equals n times p, because it is binomial and this is the formula. Why it's binomial? Because here I have two outcomes, either it is defective or not defective, but it's not just one item, but it's repeated for 2000 items, so it is binomial, and the expected here value is n times p. In since we say we can use the approximation, if we want to use the approximation here, we need to replace the expected, which means here we replace binomial by Poisson, so we replace the expected value by lambda, which is n times p. It equals lambda here equals 2000 times 0.001. We get 2. This is our lambda. Now let's use the binomial formula. Let's use the Poisson formula. You will see that the result is almost the same. Let's calculate the probability that px equals 3, which means the probability of getting 3 defective items among these 2000. So px equals 3 is, when we apply the binomial formula, it's the combination of getting 3 among 2000 times the probability of getting defective power the number of success here, which is 3, times the q, which is 1 minus the probability, power the number of failure, which means 2000 minus 3, and we got 0.1805. Now let's use the approximation. So instead of binomial, let's use the Poisson. We said lambda is 2, and we replace it in our formula, so it is exponential of 2 times 2, which is the lambda, power 3, which is the number of success here, px equals 3 divided by 3 factorial, and this is the result, which is approximately the same as this one. So whenever you have p very small, like below 0.05, and n very large, above 20, but for more accuracy above 100, instead of binomial you can simply use the Poisson distribution. Thank you for watching, and goodbye.